we're going to discuss how to use definite integrals to find areas. Let's review for a moment. If f is a non-negative function that is continuous on a closed interval from a to b, then its Riemann integral is simply the area of the region between this function f and the x-axis, just like you see on the screen. Since we have already talked about how Riemann integrals and definite integrals are different, when we want to use integrals to define an area, we should look at it as a Riemann integral, not a definite integral. Now, if the function has an antiderivative, the fundamental theorem of calculus tells us we can compute this Riemann integral using a definite integral. Since the functions we deal with here usually do have antiderivatives, we can easily just treat the area as a definite integral. In other words, we can use the fundamental theorem of calculus to find areas. This screen shows how to find the area of the region enclosed by two non-negative and continuous functions f and g over the closed interval from a to b. Let's assume that function g always stays below function f. In terms of their function values, this means the function value of g is always smaller than the function value of f. In other words, for any point x in the interval a, b, g of x is less than or equal to f of x. Since g is always below f, the area between the two curves from a to b is simply the area under f minus the area under g. This gives us the Riemann integral of f minus the Riemann integral of g, which is exactly what you see on the left-hand side of the equation in the very last line. Then, by applying the linear property we talked about earlier, we can combine them into the single integral shown on the right-hand side. In this example, we are going to find the area of the region bounded by two curves as shown in the diagram below. Check the diagram. These two curves are defined by the functions y equals f of x equals x plus 2 and y equals g of x equals x squared. In order to figure out what the bounded region looks like, we need to find the intersection points first. The two functions intersect where their y values are the same. So, we have to solve the equation f of x equals g of x, which is x plus 2 equals x squared, just like the expression on the left of the second to last line. Once we factor it, we get the equation on the right. From there, we can see that x equals -1 and 2. In other words, the two curves cross each other at x equals -1 and 2. Since they intersect at x equals -1 and 2, this also tells us that our upper and lower integration limits are 2 and -1. Over the interval from -1 to 2, since x squared is less than or equal to x plus 2, function g always stays below function f. Because of this, we need to calculate the definite integral of f minus g from -1 to 2. In other words, we integrate x plus 2 minus x squared, just like the very last line on the screen. Once we work out the integral, we get our final answer, which is the area. This screen shows that, to find the area bounded by two continuous functions f and g on the closed interval from a to b, we do not actually need to assume that both f and g are non-negative. Generally speaking, as long as the upper boundary of the region is given by function f and the lower boundary is given by function g, the integration formula for the area between them stays exactly the same, just like the very last line on the screen. We will look at how to prove this on the next slide. The proof for this is actually pretty easy to follow. Even though the functions f and g might not be non-negative, we can always find a large enough positive number c to make both f plus c and g plus c to be non-negative, just like the second line says. Simply put, we are just shifting both curves upward to bring them above the x-axis. Since we move them up together at the exact same time, the area trapped between them does not change at all. And because these new shifted functions are now non-negative, We can use our earlier rule for non-negative areas to calculate the area between f plus c and g plus c. This gives us the expression on the left-hand side of the equation in the very last line. Then, once you cancel out the constant c, you get the expression on the right-hand side. As you can see, the formula stays exactly the same. In this example, we are going to find the area of the region bounded by the two curves, sine of x and cosine of x, as shown in the diagram below. Check the diagram. First, let's find the intersection points by solving the equation sign of x equals cosine of x, which is the very first expression on the second line. From there, we solve for x and get pi over 4 and 5 pi over 4. Between these two values, sine of x stays greater than or equal to cosine of x the entire time. This means to get the area, we need to take the integral of sine of x minus cosine of x, integrating from pi over 4 to 5 pi over 4, just like the very last line shows. Once we compute the integral, we will get our final answer for the area. In this example, we want to find the area of the region bounded by the two curves y equals 4x and y equals x cubed between x equals negative 2 and x equals 2, as shown in the diagram below. Check the diagram. Before we find the area, we need to figure out which function is the upper boundary and which one is the lower boundary. For this example, we have to split the calculation into two parts. When we look at x from negative 2 to 0, the upper boundary curve is y equals x cubed, and the lower boundary curve is y equals 4x. But when we look at x from 0 to 2, it's just the opposite. The upper boundary becomes y equals 4x, and the lower boundary is y equals x cubed. So, for the first part from negative 2 to 0, we need to integrate x cubed minus 4x from negative 2 to 0. That is, the first integral on the left-hand side of the equation. For the second part from 0 to 2, we integrate 4x minus x cubed from 0 to 2, which is the second integral on the left. Adding these two integrals up gives us the total area from negative 2 to 2. Once we find the antiderivatives and work out the math, we will get the final area. Up until now, we have been looking at the area bounded by upper and lower boundaries. Now, let's talk about the area trapped between a left boundary and a right boundary. Let's assume the right boundary function is x equals f of y, and the left boundary function is x equals g of y. The formula to find the area between them is exactly what you see in the very last line on the screen. Remember, when we dealt with upper and lower boundaries before, we integrated with respect to x. But in this case, for the area between the left and right boundaries, we're going to integrate with respect to y. In this example, we want to find the area of the region bounded by a left boundary function, x equals y squared, and a right boundary function, x equals 3 minus 2y squared, as shown in the diagram below. Check the diagram. First, let's find the intersection points by solving the equation y squared equals 3 minus 2y squared. With a quick calculation, we can get two values, y equals plus or minus 1, just like the third line shows. The formula for the area is at the very last line. Here, we are integrating with respect to y from negative 1 to 1. The integrand is the right boundary function 3 minus 2y squared minus the left boundary function y squared, and that will give us the area we are looking for. In this example, we want to find the area of the region bounded by the curve x equals y squared, and the line x minus y equals 2, just like you see in the diagram. We're going to show you two different ways to calculate this area, one integrating with respect to x, and the other with respect to y. First, let's find where the two curves cross. By solving the system of equations, we get our two intersection points at 1, -1, and 4, 2. The graph is shown right below. Check the diagram. First, let's look at how to integrate with respect to x. To start off, we need to figure out what our upper and lower boundary functions are. Looking at the graph, if we integrate with respect to x, our limits go all the way from 0 to 4. So, in this interval, the upper boundary function is y equals the square root of x, which we get by solving for y and the curve x equals y squared. Now, the lower boundary is a bit trickier because it is made up of two different equations. For x between 0 and 1, the lower boundary is y equals negative square root of x, which is just the bottom half of the parabola, as you can see from the graph. Then, when x goes from 1 to 4, the lower boundary changes to the line y equals x minus 2, which is also clear from the plot. Because the lower boundary is made up of two different equations, we have to split the integral into two parts, just like the first line on the screen shows. Remember, the integrand is always the upper boundary minus the lower boundary. If we integrate from 0 to 1, the upper boundary is square root of x, and the lower boundary is negative square root of x. Subtracting the two gives us the first integral in that line. Then, from 1 to 4, the upper boundary is still square root of x, but the lower boundary becomes x minus 2. Subtracting those gives us the second integral. After doing some algebra, we get the expression on the second line. From there, we just find the antiderivatives to get our final numerical answer, as shown in the very last line. Now let's look at the other way to do this, which is integrating with respect to y. This time, our right boundary function is x equals y plus 2, and our left boundary function is x equals y squared. Looking at the intersection points on the graph, you can see that if we integrate with respect to y, our limits go from -1 to 2. The integrand is just the right boundary minus the left boundary, which gives us y plus 2 minus y squared. This matches exactly what is written in the very last line, and after finding the antiderivatives, we get our final answer.